In this video, we're going to talk about transforming graphs. It is going to be a shortcut way to create a graph of a new function from one of the functions in our library of functions. Let's consider the function x squared. X squared has been graphed in red. If we take and change the function, transform the function x squared by adding 2 after evaluating x squared, notice what happens in blue. The graph of the function x squared has been moved 2 units vertically up. Conversely, if we start with our basic function x squared and subtract 3, we look at the impact on the graph of x squared. It has now been moved down 3 units, and that's our green graph. Let's take a moment to generalize this. If you start with a function and add a constant after evaluating the function, that's going to move the graph vertically c units. If c is positive, it's going to move the graph up the y-axis. If c is negative, it's going to move the graph down the y-axis. This is subtly different. Now we're taking our basic function x squared, and we're adding 2 before we apply the squaring function. So if we add 2 before applying the squaring function, we move from the red graph to the blue graph. The graph has moved 2 units to the left. Its vertex is now at -2. So be careful. Adding 2 does not move it to the right. Adding 2 moves it to the left. The vertex is not +2. The vertex is -2. Conversely, if we take our basic function x squared and subtract 3 before applying the squaring operation, our red graph x squared is going to be moved to the right 3 units. Our new vertex is at x equals 3, not x equals -3. If we step back and try to generalize this, suppose c is a positive constant. X plus c will move the graph to the left in the negative direction. X minus c will move the graph c units to the right in the positive direction. It's a little bit counterintuitive. You would think minus c would move it in the negative direction, but minus c moves it in the positive direction. Now let's consider the impact of not adding a constant to our basic function, but multiplying our basic function by a non-zero positive constant. If we multiply x squared by 3, the red graph gets transformed into the blue graph. The blue graph is steeper than the red graph. It has been vertically stretched. So what we have is a vertical stretching of the graph, pushing it towards the y-axis. If we multiply by a larger constant, say 5, we get the green graph, which is stretched even further. It's a bigger vertical stretch by a factor of 5, and it has been stretched so that it's closer to the y-axis. To summarize, if we multiply by a positive constant, the graph will be stretched vertically by a factor of c. The bigger the constant c, the bigger the stretch, the closer the graph becomes to the y-axis. If that constant multiplier is negative, the impact of multiplying by a negative constant is to reflect the graph across the horizontal, across the x-axis. So x squared, which had a local minimum here at 0, 0, gets reflected, becomes the blue graph, which has a local max at 0, 0. So multiplying a function by a negative constant results in a reflection across the horizontal axis. So this slide summarizes all 4 transformations. The first 2 transformations are called translations. They move the function. Adding c afterwards moves it up and down, moves it vertically. Adding the constant beforehand moves it horizontally, moves it left and right. Multiplying by a constant, a non-zero constant, is a compression. It's going to compress the function. If the constant is bigger than 1, it compresses it vertically towards the y-axis. If the constant is a fraction between 0 and 1, like a half, it's going to flatten it out. It's going to compress it horizontally towards the x-axis. Multiplying by a negative reflects across the horizontal. So you have 3 types of transformations. Translations, where it moves. Compressions, which are accomplished by multiplying by a constant. And a reflection, which is by multiplying by a negative number. So we're going to step by step use transformations to graph the function minus 2 times the square root of x plus 1 plus 3. So we start with our basic function from our library of functions, square root of x. That's the red graph. You may recall that's the graph of the square root of x. As we're building towards this final result, we're going to do what's underneath the square root first, not the negative 2, not the plus 3, order of operations. Do what's under the square root first. So we're going to add a 1. Adding a 1 before you take the square root is going to move it horizontally. If you're adding 1, it's actually going to move it to the left. So this graph, this red graph, is going to move to the left 1 unit. This is this blue graph, the square root of x plus 1. Then we're going to evaluate what happens when you multiply by 2. That transformation is the vertical compression. So this blue graph gets compressed vertically and becomes steeper. That's the green graph. Then we're going to multiply by negative 2. The green graph gets reflected across the horizontal. Then we're going to take that purple graph, namely the minus 2 square root of x plus 1, and move it up 3 units. So the purple graph is going to get moved up 3 units, and here is our final result, the orange graph. And we graphed it not by plotting points, but by using transformations. A transformation that shifted it to the left, that compressed it, that reflected it, and then moved it up 3 units vertically.